So one final case of being able to work with these second order differentials that are non-homogeneous with the repeated case. So this time we're going to take a look at this differential. Third derivative of y minus 2 times the second derivative of y equals 3x plus 5. Now this is one of those anomaly cases that even if you do add the next x, it's still not going to work out precisely. So let me show you if you were to do the regular process. So we're going to do what we did for the other 6 examples. We're going to start with the characteristic equation. So m cubed minus 2m squared equals 0. M squared m minus 2 equals 0. And notice that we get a double root. So m1 equals m2 equals 0, and then we get a third m, which is going to be 2. So our complementary solution is going to be equal to c1 e to the 0x plus c2x e to the 0x, and then plus c3 e to the 2x. And so we're going to guess a particular solution. And because we have a linear term, we would guess ax plus b. All right. Now, if we simplify the complementary solution, we'll notice that there's going to be some repetition there. Because notice that c1 e to the 0x just simplifies to c1. c2x e to the 0x just simplifies into c2x, and then we still have the c3 e to the 2x. And I want you to notice that, okay, well, c1 is a duplicate of b, and also that c2x is a duplicate of ax. So unfortunately, we're going to have to go up a little bit higher. And so what we might guess is we might guess that the particular solution look like ax squared plus bx plus c. And although that's the technique that we should use, let's see what happens when we start taking successive derivatives of this. So if we take the first derivative of the solution, that's 2ax plus b, and that's okay. Second derivative, 2a. But then unfortunately, if we take the third derivative, that's 0. And that doesn't make any sense because we need to substitute something back into that third derivative to be able to eventually get to 3x plus 5. All right, so unfortunately, we're actually going to have to go up to ax cubed because of that. All right, so let me erase all this. And we're going to change the particular solution one last time. All right. So let's change the particular solution to ax cubed plus bx squared plus cx plus d. And when we start finding the successive derivatives, we just need to make sure that we have enough so that the original differential will stick around. All right, in other words, it doesn't go to 0. So we're going to have 3ax squared plus 2bx plus c. Second derivative, 6ax plus 2b. And then third derivative, 6a. And now we're going to substitute those back into our original differential. All right, so remember the original differential, y3 minus 2y double prime equals 3x plus 5. And I'm just going to check that just to make sure. And so when we substitute back in, this is now going to become 6a minus 2 of 6ax plus 2b, and that's going to be equal to 3x plus 5. And now it makes more sense. All right, the way it was before, remember y double prime, I believe, was 2a. We would never have an x term. So we need to make sure that after we take 3 derivatives that we're still left with some x term when we substitute back in. Right? A little bit of distribution, we wind up with 6a minus 12ax minus 4b is equal to 3x plus 5. Coefficient of x has to be equal to coefficient of x. And then also, the other constants have to be equal to 5. Right? And this is an x, not a lambda. So when we go through and we get our solution through the system at least, so our system, one of them is going to be really easy. We get negative 12a is going to be equal to 3. And then we get 6a minus 4b is going to be equal to 5. Clearly, a is negative 1/4 from the first equation. And then if we substitute negative 1/4 back in, 6 times minus 1/4 minus 4b equals 5. Right. And when we solve that, I'm just going to solve it really quickly so that way we don't have to suffer through this. So I wind up with negative 13/8. All right, so now we finally have our particular solution. So remember yp, and then it doesn't say anything about c or d, and that's okay, because remember, cx is the same thing as c2x, and d is the same as c1. All right, so we really don't need those, but I'm going to show you what happens for this anomaly sort of problem. So yp is going to be equal to, and it kind of contradicts the idea of a particular, negative 1/4 x cubed minus 13/8 x squared plus cx plus d. Right? And so y of x, which is going to be equal to yp plus yc, is going to be equal to what we just had above. So 1/4 x cubed minus 13/8 x squared plus cx plus d. And then remember we had the complementary solution, c1 plus c2x plus c3e to the 2x. All right, now, to finish this off, notice that c1 and d are both constants, so we can meld that into a new constant. Notice that c2x is the same thing, or at least has the same term as cx. So we would usually just combine these together to be able to get a final solution, and the final solution to this is going to look like 1/4 x cubed minus 13/8 x squared. I'm just going to call it c4x, and then I'm just going to call it c5, and we're going to have plus c3e to the 2x. All right, I'll just put a little note down here that c5 is going to be equal to d plus c1, and then also that c4 would be the sum of c and c2. All right, but this is the solution to the differential. Of course, you could find two derivatives of that, substitute it back in to the original differential equation, and then see if it works. All right, so just one of those anomaly cases I wanted to make sure that everybody understood as to how to go through and try to solve those types when, if you keep taking successive derivatives of your polynomials and the repetition occurs, that you might have to go up higher than just one power.